permutation of, well, that's not working. Permutation of n items taken r items at a time is equal to n factorial over the difference of n and r factorial. And so in this case, n is 18, r is 3, so we have 18 factorial over 18 minus 3 factorial, which is 18 factorial over 15 factorial. I'll expand that. 18 multiplied by 17 multiplied by 16. We wouldn't want to go all the way to 1, but we recognize that 15 factorial, or 15 times 14 times 13 all the way to 1 is the same as 15 factorial. And since I have 15 factorial in my denominator, I can stop there, because whatever that long product is, it will, when I divide it by this product, this equivalent product, they'll equal 1. So I'm just factoring out 1 whole by doing that. So we need to do 18 multiplied by 17 multiplied by 16 to find the answer. It's okay to use a calculator for that. Uh, 4,896. Problem number 6 says a test includes several multiple choice questions, each with 5 choices. So you may have answer choices like A, B, C, D, and E. Suppose you don't know the answers for 3 of these questions, so you guess. What is the probability of answering incorrectly on at least one question? This is extremely, let's see. It's possible to do this lots of different ways, but many of them are very time intensive, labor intensive. You have huge tree diagrams, for example. But unless you realize something, this event is complementary to a much simpler event. So let's read the event again. What is the probability of answering incorrectly on at least one question? If you don't answer incorrectly on at least one question, what must have happened? If this doesn't happen, what must have happened? If you don't answer incorrectly on at least one question, you must have answered correctly on all 3 questions. And that's very easy to calculate. So the probability that you'll guess correctly 3 times in a row is not too hard to calculate, and then we can use our understanding of complementary events to find the probability that you'll answer incorrectly on at least one question. The probability of answering correctly on all 3 would be the product of the probability of answering correctly on the first question multiplied by the probability of answering correctly on the second question multiplied by the probability of answering correctly on the third question. And these events are independent, because the probability of answering correctly on the second question is in no way influenced by you guessing correctly or incorrectly on the first question. So if there are 5 answer choices, there's a 1/5 probability of answering correctly on this question, multiplied by a 1/5 probability of answering correctly on this question, multiplied by a 1/5 probability of answering correctly on this question. That product is 1/125th. You then just need to realize that the probability of answering incorrectly on at least one is equal to 1 minus the probability of answering correctly on all 3. Because I'm either going to answer correctly on all 3, or I'm going to answer incorrectly on at least 1. I might answer incorrectly on all 3 of them, I might answer incorrectly on 2 out of 3, but either this or this must happen, so they have to add up to 1 whole. So if we just do 1 minus the probability that we just calculated, 1/125th, we have 125 125ths is 1, minus 1/125th, so the answer is 124 125ths. I shouldn't have circled that. This is our final answer right here. Problem number 7. A box contains different color paper clips. The box contains 3 red, 4 yellow, 5 green, and 6 blue paper clips. what is the probability of reaching into the box and selecting a red paperclip? That's just a simple event. It's just favorable outcomes compared to possible outcomes. There are 3 red paperclips, and there are altogether 3 and 4 is 7, and 5 is 12, and 6 is 18. So there are 3 favorable outcomes. It's probably not the best color. Let's see. 3 favorable outcomes, and 7, 12, 18 possible outcomes. You should always simplify your probability if you can, so that's 1/6. I'm in the wrong section too. Okay. 3 favorable outcomes, 18 possible outcomes. That simplifies to a probability of 1/6. What is the probability of reaching into the box and selecting a paperclip that is not yellow? I'm going to use the same idea we used on the last problem and think about complementary events. The probability of selecting a yellow paperclip is 4/18. So the probability of selecting a paperclip that is not yellow must be 1 minus 4/18 or 14/18. 14/18 simplifies to 7/9. You could have also added up all the ones that are not yellow. There's 3, 5 is 8, and 6 more is 14. So that's another way to do it. Next question says, what is the probability of reaching into the box, selecting a blue paperclip? I'm going to underline this part. This is important. Then putting the blue paperclip back in the box. Then reaching in the box and selecting a red paperclip. Because we're putting the blue paperclip back in the box, it resets the situation, and the probability of selecting that red paperclip is not in any way influenced by the fact that we pulled a blue paperclip the first time. So these are independent events. This is going to be equal to the probability of blue multiplied by the probability of red. The probability of blue is, we already answered this question. They're independent because the paperclip is put back into the box. Probability of blue is 6/18. The probability of red, we already calculated up here, is 1/6, or 3/18 or 1/6. I'll just write it as 1/6, and then we can factor out this whole, these 6/6, and we get a final probability of these 2 events occurring of 1/18. Problem number 8. How many triangles are determined by 9 points if no 3 of the 9 points are collinear? Collinear means on the same line. So if I just start putting points down, it's really hard to, with 5 points, I don't think, of course, any 2 that you choose are collinear, but there are no 3 on the same line. These 3 are close to being on the same line. But as you start to add more and more points, it becomes really difficult to make sure no 3 are collinear, unless you realize that putting them on a circle guarantees that they're not collinear. No more than 2 of them at least. That's something like a circle. Okay. So here are my 9 points. It'd be easy to put 8. I would know exactly how to space 8. I don't know exactly how to space 9. Except, I need 6 more so I can, that's not terrible. Okay. You don't have to go to these lengths. There's a more direct approach to this, but I want to illustrate what's going on here just to make sure we're clear on a key point here. Any 2 of these, let me show you an example. I can draw a line through these 2. I can draw a line through these 2. But there's no line that I can draw that will go through 3 at a time. And so that's what it means by no 3 of the 9 points are collinear. Now that we have the 9 points, I'm going to label them A, B, C, D, E, F, G, H, and I. Okay, now I'm going to randomly select 3 points, draw a triangle, and go from point A to point G, from point G to point D, and then from point D back to point A. And this triangle could be named triangle ADG, or I could name it triangle DGA, triangle GAD. All of these, doesn't matter how I name it, I'm still talking about the same triangle. So does the order of these letters matter? No, it does not in this case. And so all of that was to explain that the order does not matter. And if the order does not matter, we're not dealing with a permutation. In a permutation, the order does matter. In a combination, the order does not matter. So I have a combination of 9 points, taken 3 at a time to draw need 3 of them to draw a triangle. And so the combination formula is at the bottom of each review page, but it is this right here. It's the combination of n items taken r items at a time is n factorial over the difference of n and r factorial. Right up to this point, it's just like the permutation formula, but we also divide by r factorial. And so in this case, n is 9 and r is 3. So we have 9 factorial divided by 9 minus 3 factorial multiplied by 3 factorial. I'm going to expand this, and I'm going to stop here when I get to 6 factorial. Well, actually, let me show that first. 9 factorial over 6 factorial, 3 factorial. I'm going to expand this, but I'm only going to go up to, when I get to 6, everything after 6 is going to be 6 factorial. So I'm just going to show 9 times 8 times 7 times 6 factorial over 6 factorial. Now, because those will cancel. But don't make the mistake of don't just write 3 factorial. A lot of students are writing 3 factorial and then treating it like it's 3. 3 factorial is 3 times 2 times 1. You need to cancel out the 6 factorial, and then you need to cancel out factors to get rid of this 3 and this 2. It's been a very common mistake to just leave it as 3 factorial and then just make this 3. You'll end up with a result that's twice as large as it should be if you do that. So the 3 and the 9 have a common factor of 3, so I'm going to factor out those 3/3. The 8 and the 2 have a common factor of 2, so I'm factoring out those 2 halves. And what I'm left with is 3 multiplied by 4 multiplied by 7, which is 12 multiplied by 7. So that's 84 possible triangles could be determined by 9 points where no 3 of the points are collinear. Okay, that does it for page 2. I hope that helped. We'll pick up the review with